this is called, this section 5-5, 5-5 is called linearization and differentials. Okay? And differentials, and I assigned some homework on differentials, but I do not think I'm going to get to it. So we're going to spend, I originally was going to only spend 1 day on this section, but there's a lot of stuff in here. So we're going to spend 2 days on this section, and we're going to spend 2 days on related rates. Yeah, we're going to spend 2 days on this, which is 5-5. 2 days on related rates, which is 5-6. And then 2 days on review, hopefully, or a day and a half really on review.
So there's no quiz on the second part?
No, just because I want to give you guys a test. Maybe I'll give you a quiz and then a test later. I'll think about it. I want to look at the rest of the calendar and see. Because, whoops.
Sometimes it's hard to just go straight into the test.
Yeah, it is.
So where is the other administrated?
I don't, sorry. No. Almost. I'll have it by Wednesday at the very latest. But hopefully by tomorrow. They go pretty fast. I just what? 1.5. How? Not so great. This isn't your best quiz, guys. But I would like to give them back to you so you can see what you did wrong so you can do better on the test, right? Okay. So, linearization and differential. So the idea behind this is that if you have a curve, okay, some arbitrary curve or some function going like this, as you get very close to some value on the curve, right, it's called focal linearization. As you get very close to a point, if you were to zoom in on that point, the curve would look more like a line. Do you understand that kind of? So if you get very, very close to, this point, if you keep zooming in and zooming in, right, it ends up looking like the same thing, really. Okay, and that's why they thought Columbus was crazy, because they were way zoomed in when they were looking at the world. You know, they didn't have like airplanes and stuff where they could zoom out and see that the Earth actually curves. You know, so like the idea that if you get very close to a curve, it looks like a line. That's the idea of local linearization, and they use that to make approximations for things. Okay, so there are, even though it seems very mathematically theoretical, there are some applications of it in that you'll see in a minute. So then I type this out, and this is basically what they say in the book. If f is a differentiable function at a, then the equation of the tangent line, L of x, equals f of a plus f prime of ax minus a. This is the equation of the tangent line. They just moved the y1 onto the other side, right? It's point slope form, but they moved the y1 onto this side and it became a plus, right? See what they did with that? And so this is the equation of the tangent line, and it defines the linearization of f at a. Then f of x is approximately equal to L of x at x equals a. That should say L of x. It's L of x at x equals a, where a is called the center of the approximation. Okay? So if you want to write that down, you can. If you just want to look at it and take in those words, that's okay too. You want a minute to write that down? It's in your book. I kind of. So in this case, what they do, let me shut the door. Okay? I just sounded like Barack Obama when I said,
Let me shut the door.
when I he has that deep voice. Anyway, where was I? Uh-oh. I got confused. I was like, oh, because I digress too much. So, in any case, Find the local linearization of f of x and use it to approximate 1.02. So the square root of 1.02, because this can be thought of as the square root of 1 plus 0.02, right? So if I use the function 1 plus the square root of x, which kind of looks like it's a square root function, and it starts here at -1, and it goes like this. So when x is equal to 0, what I'm going to be doing at x equals 0, I'm going to find the tangent line at x equals 0, right? If this is the graph. And if I go 0.02 away, am I recording now? Yeah. If I go 0.02 away from 0, I should get a very close value to that function. Do you understand what they're doing here? And you say, why not just plug into your calculator and get the answer? Yeah, you could do this, but this is a way to get approximations of functions like this, of sort of complicated functions, values, without having to use your calculator, because you could use numbers that come out nice, and then you can come out with a linear equation, which is easy to plug into rather than doing like a square root equation or something like that. Yes, ma'am?
Do you know 0.02 away on the tangent line?
Both, same thing. Yeah, it's going to be the same. I mean, the 1.02. So what this idea says is that the value of when I plug in 0.02 into the function or for x, and what the value that I plug in for 0.02 into the tangent line, they're going to be very, very close to each other. Okay? And that's the idea that this whole thing is based on. So all you have to do is first you have to find f of a. Okay? And f of a, if this is f of x, what do I get when I plug in 0 in there? What's f of a? What's the square root of 1 plus 0? 1. You can do it. 1. All right? Now I have to find f prime of a. And so the way I do that is taking the first derivative of f prime of x is equal to 1/2 times 1 plus x raised to the -1/2 power, which is the same as 1/2 square root of 1 plus x. So that's f of x, f prime of x. So what's f prime of a? If I plug in 0 in there for x, I get out 0. So what do I get out? I mean, I plug in 0. I get out 1/2. So this is the slope of the tangent line. This is the y value at the tangent line, and the x value is just 0. Okay? Or excuse me, and the f of a is 0, but I have to plug in the x value that I'm looking for. So anyway, so what I get is L of x, which is the linearization of this line at some point, is equal to f of a, which is 1, plus 1/2 of x minus a. What's x minus a? What's x minus a if a is 0, right? With f, what's a? Or excuse me, what's x minus 0? X, right? So I want L of 0.02. So in other words, I want to plug in 0.02 in for x. So I'm using this is an equation of the tangent line at x equals 0. And what I'm trying to do is use this tangent line to approximate when x is 0.02. So if I go 0.02 this way, I would be finding the square root of 1.02. So this would just be, sorry, just stuttered it, 1/2 times 0.02, which is just 1.01, I think. Okay? Now look, if you take your calculator and you do take the square root of and if you do take the square root of what was it? 1.02 second square root of 1.02, I get a number that is very, very close to 1.01, but not exactly the same. You see that? Okay. So you say your error is within, it's actually within 0.0001. So they say the error is less than 10 to the negative 4th power, which is pretty small. And the way I find that error is by subtracting 1.01 minus this and taking the absolute value. All right? Questions on that? Far? Okay. So now, what time do we got here? What time do we get up? 10 after? 5 after?
No.
Yes.
So, Mr. Leader, is that just the answer? What's the answer?
That is the answer.
1.01.
1.01.
So that extra step at the end was just to check.
Just to show you.
Okay.
And sometimes I'll say, what is your error? Okay, from
And
the actual value.
if they ask you what's the error, you just subtract the two.
Yeah, you subtract and take the absolute value. Because
Okay.
the
Okay.
error is a positive. Funny. Okay, so I'm going to jump ahead. I was going to do some other types of ones, but I want to talk about a different type of place where you might use this. So use f of x equals the cube root of x at to approximate the cube root of 123. And use local linearity, use local linearization, I'll call it linearization, to find that. All right? So cube root of x, I believe, looks something like this, and 123 is going to be somewhere out here, okay? And you don't want to, you want to try to do this without a calculator. You say, how the heck do I do that? Well, you try to find a number that is fairly close to 123, which you can take the cube root of, 125, okay? So you try to find a value that's pretty close to that, okay? And you call that a. A equals the cube root, and usually they'll tell you what number to use, but a is equal to 125, okay? Because I can take the cube root of 125, even though I can't take the cube root of 123 very easily. So what I do is, I know what f of x is. F of a is going to be the cube root of 125, which is 5, okay? And now I got to find f prime of a. So I have to take f prime of x, and f prime of x, if I look at this, is 1/3 x to the negative 2/3, right? I subtract my exponents, and that's like x to the 1/3. So that's equal to 1/3 x to the positive 2/3. So now f prime of a, God bless you, f prime of a is what I get when I plug in 5 in there. And if I plug in, not 5, 125 in there, 125, and I get out, the cube root of 125 is 5, squared is 25, times 3 gives you 75. See that? So I get 1/75. So what that's saying is at 125, the slope of my tangent line is 1/75. And the y value is 5. So I'm going to use the function L of x. I'm going kind of quick because I want to get through it. L of x is equal to 1 over 75 times, whoops, sorry, I forgot my a, is equal to a, which is 5, plus 1 over 75 times x minus a, and in this case, a is what? 125. So this is my equation of the tangent line at this point, okay? And I'm going to use that to approximate the cube root of 123, so I'm going to plug in 123 there. So very close to 125, the curve looks like the tangent line, all right? So L of x is going to be equal to 5 plus 1 over 75 times negative 2. Right? Because that's 123 minus 125. And if I do that on my calculator, I get, don't go away yet, 4.973. And you want to take this to pretty many decimal places, 4.973. And then again, 9739975. And then again, if you did that on your calculator, okay, the square root of, cube root of 4.973, just to see how far off I am. You're really close, okay?
What are you close to?
To the cube root of 123. So this value would be very close to the cube root of 123. So you're using a line to find that value rather than the curve. So probably you're not going to be able to finish all the homework because I didn't get to everything. I'll finish talking tomorrow and add on a few more problems, okay? But you can get started on it if you want to read the book. Yeah, the whole thing will be due on